Hello everyone and welcome to Complex Analysis. Today we are going to explore a new way to represent complex number, the polar form. Now we are all familiar with writing complex numbers as x plus iy, where x and y are real numbers. But what if we wanted to describe the same point in terms of distance and direction instead of horizontal and vertical positions? By switching from rectangular form to polar form, we are not only describing number differently, but also making the operations like multiplication, division, and exponentiation much simpler. So let's get started by revisiting the complex plane and see how complex number can be expressed in terms of r and theta. Recall from calculus that a point P in the plane whose rectangular coordinates x and y can also be presented or represented in polar coordinates. Polar coordinates consist of the points O, which is the pole, and the horizontal half line emanating from the pole, which called polar axis. The point in this coordinates, P, has r and theta. R is the direct distance from O to P, and the theta here is the angle of inclination theta. So in fact, being able to switch between rectangular and polar form of a complex number is extremely helpful because it gives us flexibility. Many operations like multiplication, division, and finding powers become much simpler in polar form. So how we can switch from those coordinates? Let's see. If you have it this way, if you have a point here P, which is x and y, I have two copies, maybe r and theta as well, and this is and here this is r, and this is of course the distance from here is x, the distance from here is y, and this is theta. So and we have it here. This is the angle, the right triangle. So the sine theta, which is the opposite y over the hypotenuse, and the cosine is sine theta equals the adjacent x over the hypotenuse r. And from here, which implies y equals r sine theta, and here which implies x equals r sine. Since in rectangular coordinates or in the rectangular form, the way we represent the complex number z as x plus iy, so we have the polar form as r sine theta plus r plus I r sine theta, which equals r sine theta plus I sine. This is the way we represent. This is the way we represent complex number in polar form. And of course, to find this, we need to know to switch between them. R equals the z squared, the length, the distance, which is in this right triangle, we have it as x squared plus y squared, and theta equals a tan inverse of y over x. And we keep in mind that tan is pi periodic, so whenever it happens, we need to be careful to see where is the complex number is located in which quadrant. And of course, from here we find theta and r. From here we can find x and y. So we can switch between the polar and and rectangular forms. Let's see how we do it. Example, express this complex number in polar form. As we see here, x equals negative the square root of 3 and y equals -1. And as a result, r equals the square root of the square root plus y squared, which is the square root of the square root of 3 cubed plus -1, -1 squared, which equals 3 plus 1, which equals square root of 4, which equals 2. And for theta, it is tan inverse y over x, which is tan inverse -1 over the square root of 3, which is tan inverse 1 over the square root of 3. And it is a very common one. It is the angle of pi over 6. So if we need to see it, we need to be careful since the rectangular form here, this is the number here. And in fact, this is pi over 6. Since the number we have is -3, the square root 3, the negative square root 3, and 1, -1. So it is here, in fact. The point is here. Since it is pi periodic, so it is here. So this is 1. We add pi. We add pi, which is 7 pi over 6. Because it is pi periodic function in the tan. So this is pi over 6 and plus pi plus pi over 6, which is equals 7 pi 6. And as a result, to answer the question, z equals r sine theta I sine theta plus I sine theta, which is 2 sine pi over 7 plus I sine pi over 7. Amazing. And now we need to, in this example, we saw how we can switch between polar forms to polar form. But why it is powerful? In fact, it is really powerful to represent complex number in both ways, because polar form makes some operation much simpler. And to see the motivation, let's if you've been asked to find the z cubed and you've been given that z equals the previous number, negative square root of 3, negative I minus I. So to find z cubed, we need to have a negative square root of 3, negative I, all to 3. So it is quite a big expansion to do, but if we use the polar form, like this is a rectangular form, we switch it to polar form, it would be much easier. This is the motivation here. And before do this, I want to share a small story how this has happened. If we have z1 and we have z1 in polar form, like r1 sine theta 1 plus I sine theta 1. This is a complex number, and this is another complex number. This equals r2 sine theta 2 plus I sine theta 2. We have two complex number in polar form, and z1 multiplies z2, which is r1 r2. We have sine, and this is we have distribution here, sine theta 1 sine theta 2 plus sine theta 1 I
sine theta 2 distribution, this one and this one, this guy, and plus I sine theta 1 sine theta 2, and this one multiplied by this one, plus I squared sine theta 1 plus sine theta 2. And we close it, which is here. We have it. We have here. Have this one as a negative -1. So we have the real part, the imaginary part, cosine, cosine, sine, sine, and we know this is it's very clear that R equals summation of sum of angles, which is theta 1 plus theta 2. I mean this one and this plus I here sine, cosine plus cosine, sine, sine, cosine, sine, sine, which is the sum of angles, sine function, sine theta 1 plus theta 2. This is very beautiful results. So if we need to expand this and to higher dimension, we can see that z squared. I'm not sure. I'm not saying for higher dimension. I mean to higher degree. Z squared equals r squared sine 2 pi 2 theta plus I sine 2 theta because we have the same r multiply r squared, and theta plus theta is the same 2 theta y. So let's see how it happens here for this for two complex numbers. We have z1, we have z2. This theta 1, and this is theta 2. R1 multiply R2, the length here, or distance here, direct distance R1, R2, and the angle of inclination is theta 1 plus theta 2. The polar form shows us that the nature of the complex number multiplication, that the phase and magnitude, the length we multiply, and for angles we add. And it happens for z squared, and also it happens for zn, which is rn cosine and theta plus I sine n as well. So now it shows us why it is powerful. And back to answer this question, we have the polar form for this one, which is c equals 2, because we solved it previously, sine 7 pi over 6 plus I sine 7 pi over 6. And now z cubed equals 2 cubed sine 3 7 pi over 6 plus I sine 3, which is here n, which is here n, which is here also n, 7 pi over 3 over 6, which equals 8 sine 7 pi over 6 plus I sine, sorry, this over 2, this over 2 sine 7 pi over 2. And this is for 0. And this is -1. So we have 8, 0 plus I -1, which equals negative 8 pi. So it is much easier if you compare it to have 100, for example. So you don't need to do much as expansion, just we have to substitute 100 here. And thank you so much. We summarized the class, and we have it. We saw how we represent a complex number in terms of polar form, and we see how to switch between them, and we saw how it's powerful by expressing in terms of example, and this is the motivational example to encourage us to use the polar form. Thank you so much, and we carry on. We have a call for action. How about z 1 over n as the roots, and we have the challenge to express or to see how the fundamental theorem of algebra works for complex numbers and complex variable. And that's for today. Thank you.